Okay, now we're into Unit 2. Unit 2 is really all about forces, and some of this will be review, some of it will be kind of new, the way that we approach this stuff. We are going to start right away in 2 dimensions, and let me say at the outset that free body diagrams are very, very important. I talked before about drawing the diagram. Always draw a picture, a diagram, something you need to picture it, but that's also true for free body diagrams. The last 2 years on the midterm, there was an open-ended question, a real AP open-ended question, and both years most of the class got it wrong because they made one little mistake in how they drew the free body diagram. If you can draw a good free body diagram for each of the objects in the system, right, or for the whole system, whatever it is, that will greatly simplify the problems. Also, a lot of times, even if you're not asked to draw a free body diagram, drawing the free body diagram might get you some points. So it's always worth it to do a quick free body diagram. And we'll talk about those rules in a little while, but the basic rules are: 1, there's one object for each free body diagram. 1. And it's a box, a circle, or a dot. And the lines always come from the box, either from the center or from the surface, but they have to be touching the box if they're on the surface. There have been debates as people are grading the AP tests, if there's that much space between the box and where the arrow begins on the force arrow, do they give them credit or not? So, and then it'll depend on that year who's in the room and what the graders decide about that. But free body diagrams are very, very important, and it may have even been an issue for you on the summer assignment, so make sure you pay attention. Okay, so the first unit was all about motion, describing motion. That's all we've done. Now we want to say what causes motion. What causes a change in motion? And what is a change in motion but acceleration? So unbalanced external forces create acceleration. Right? There can be external forces, but those don't necessarily create change in motion, because if they balance each other out, then the acceleration will be 0. That's why the classic formulation of Newton's second law, objects at rest stay at rest, and objects in motion stay in motion unless acted on by an external force. That's Newton's first law. That's not necessarily true, because there can be external forces and the object still remains at rest or remains at a constant velocity. So we need to keep in mind what we mean, that we're talking about the net force. Classical mechanics, that's what we're talking about here. It's valid for objects that are much larger than atoms and where the objects are traveling much slower than the speed of light. When you're dealing with really tiny objects, that's when you need quantum mechanics, and we're not doing that in this course. And if you get things faster than the speed of light, or not faster, that's not possible, but close to the speed of light, then you need special relativity, and we're not doing that in this course either. Some special relativity is covered in AP2, but if you're watching this video, then you're not signed up for that course, so too bad. Force. So force is a vector, magnitude, and direction. Direction matters for a force, so keep that in mind. It's an interaction between two bodies, right? A body and its environment. What in the environment? Right, some other object. So whenever you draw a free body diagram and you're drawing the arrows, you got to think, what is the object that's exerting this force? And so the sum of all forces acting on the body is the net force. If the net force is 0, then it's 0 acceleration, it's a constant velocity, and we say that the body is in equilibrium. And for now, we're going to call it equilibrium. Later on, when we introduce rotation, then we would say this has translational equilibrium. That's linear movement, as opposed to things rotating. Right now we're dealing with point-like objects, and so we're talking about translational equilibrium. Right? Newton's first law: if there's no net force, so there can be forces, but just 0 net force, then the object, if it's at rest, it remains at rest, but if it is moving, it'll have a constant velocity. Second law, F net equals ma. This equation is the nuclear reactor of all of physics. It's when I was in college with my other physics nerd majors, we used to joke, if you don't know the answer to the question, you just write F equals ma. That's it. And I've had students do that on tests. They write F equals ma, and sometimes they actually get a little bit of credit, like no other response, but they just write F equals ma. Turns out, if that's one of the equations that you need to solve that problem, then you get a little bit of credit. Newton's third law. The idea here is that when two objects interact, then they exert equal and opposite force on each other. And it can be written as the force of A on B is equal to the negative force of B on A. Right? So you can switch those. Some vocabulary: mass, Mass actually can't be defined. It's that which is measured in kilograms. It's a fundamental characteristic of a body relating to how much stuff there is. System is a collection of two or more bodies. All right, so whenever you're looking at a problem, you want to decide what's my system here. Specify what are the objects that we're talking about. That'll be especially important when we get to energy, but it's also important here. External force is any force coming from bodies that are outside the system. Internal force are any forces between bodies inside the system. Net force, sum of all the bodies. Free body diagram, picture of one of the bodies and all the forces acting on it. There are contact forces, there are field forces. Contact, obviously things are in contact. Field forces, these can pass through empty space, things like gravity, electricity, magnetism. And the unit of force is a Newton, kilogram meter per second squared, which you should know. Different types of forces, gravity and weight. Right? Gravity is universal, it's anywhere in the universe. Weight, we're talking about the net force required to prevent a body from falling freely. Right? So weight would kind of be like the force the floor exerts on you to hold you up. Normal force is the force of the floor. That's the actual force of the floor. The weight is just the amount. Tension is a force from a rope or a cord. Sometimes even we talk about a spring having tension in it. Spring force, Fs, right? Force from a spring. Drag force, resistive force. We're going to get into that a lot more in a later unit because that involves some calculus that we're not quite ready to jump into yet. Friction, we have static and kinetic. Centripetal force, that stuff's going to get interesting. That is probably the most challenging part of this unit when we get to it. And important thing to note here, centripetal force is not, like the others, a kind of force where it's coming from an object. Notice centripetal force is just telling you the direction of the force. It's not specifying the object. As a result, centripetal force, this is important, listen, centripetal force never goes on a free body diagram. Never. Because in a free body diagram, you're drawing the interactions between the objects. So the centripetal force can be provided by, say, gravity, if we're talking about a planet going around the sun, for example, or it can be provided by a string, which would be a tension force. So there, the tension provides the centripetal force. Right? Really what centripetal force is, it's a net force. It's a sum of forces together, because it could be more than one thing, creating that curved path. And then there are fictitious forces, things like centrifugal force, and we'll get into more of that later. Force of gravity, right? Newton posited that all bodies in the universe are attracted to all the others. And by the way, as a historical note, when he first said that, it made no sense. And it really doesn't make any sense to us still today, but we have equations that can describe it. The idea that something 90 million miles away, like the sun, could exert a force on the Earth, like how does it do that? Through empty space. And so that's why it was such a radical idea. It was such a huge leap. But that idea has led to a lot of advances and has been able to move science forward. So we use it. Right? Gravitational, it's a field force. The superposition principle applies, by the way. So if I have more than one body, that I add up the forces. Fields, right, means by which two objects exert forces on each other. So we talk about the gravitational field of the sun. That's, you say, oh, that's how the sun exerts a force on the Earth, which is true in terms of the way that we describe it. But fields are not things. You couldn't look through a telescope and see a field. You can't do, you can't look under a microscope and see a field. You can't touch and feel a field, right? It's a mathematical construct that we've developed to help explain these forces and describe them. And the force is always there no matter what the medium is. So we talk about tension. And so here, with our example here of the monkey in the elevator, tension in an elevator, right? For part A, if there's no acceleration, that means that the tension is equal to the force of gravity. This, by the way, is a free body diagram. Right. So then for B, if it's upward acceleration, that means that T is more than Fg. Oh, see that? I need to make that connect. Okay. So T is greater than Fg. And then if it's accelerating downward, that means that T is less than Fg. Right. Now, by the way, here, this doesn't mean it's staying still, this doesn't mean it's going up, and this doesn't mean it's going down. What we're talking about here is the acceleration. This one is not accelerating, this one's accelerating up, this one's accelerating down. But this one might be moving down, right? It might be moving down but slowing down. This one might be moving up but slowing down. The net force only tells us about the acceleration. It doesn't necessarily tell us about the velocity. So we need to keep that in mind. Translational equilibrium. This is what we're talking about, things moving linearly. If they're in equilibrium, then there is no linear acceleration. All right. Later on, we'll talk about rotational equilibrium, just so you can, why are we calling it translational instead of just equilibrium? The acceleration of the body is 0 and the velocity is constant. All right, this should be all very familiar. Equilibrant and equilibrium. If I want to know, if I have some forces acting on a body, and I want to know what force can I exert to put the object in equilibrium. Let's say it's out of equilibrium, but I want to say where would I add a force to put it into equilibrium. That force that you would add is called the equilibrant. Equilibrant, right? It's there in the notes. You might see that word, so it's important to know what it is. It is the force that will put a body into equilibrium. Okay, and so here's the idea. There's a force here. It's 3 by 4. Let me put it up on the board. Okay, so I've got these two forces. I'll describe this. So F net is 3 newtons J plus 4 newtons in the I direction. And I could probably switch that, but we'll leave it for now. So the sum of these forces, the magnitude, is going to be 5. So what force do I have to add to this in order to balance these two? Because right now this is out of equilibrium. If I add a 5 Newton force this way, then that'll work. So the equilibrant, F EQ, let's say the equilibrant force, it's just the negative of these two. I would need negative, let's say negative 4I minus 3J newtons. This is the force that's going to equalize this one. And then if I add this force to this situation, then I have an object that's in equilibrium. This is the equilibrant. Okay. Applying Newton's laws, draw a simple, neat diagram. Then isolate the objects, draw the free body diagram. This is general way of solving these. Assign the x and y directions, right? Again, if you use the conventions that this is positive x, this is positive y, out of the page is positive z, then you don't have to specify. But you can change x and y, and we will do that at times, so we need to specify that. Then we use F net equals ma, solve equations, check for unknowns, and then we check for the reasonableness. So if I have the same force, example 1 now, acting on two bodies, m1 and m2, in a frictionless environment, producing accelerations of a1 and a2 respectively, find a2 as a function of a1. Right. This will be pretty simple. So what do I have here? It's the same force, F, and it's acting on two bodies, so m1 a1 equals m2 a2. So this is the mass and acceleration of one of the bodies, this is the mass and the acceleration of the other body, and they're both equal to each other because it's the same force that's producing both of these accelerations on these objects. And I want to find a2 as a function of a1. Well, here it is, right? a2 is equal to m1 over m2 times a1. That's it. That's all we're looking for in this problem. And so then example 2, let's take a look. So we have two forces. All right, so here it is. This is the free body diagram. It's a 5 Newton body. and there is a 10 Newton force this way, and then there is a 12 Newton force going this way. All right. Right now this is a free body diagram. In order to solve this, of course, what I have to do is now get rid of these and find the components, right? So this is going to be, if this is 45 degrees, right, this is going to be 10 sine 45. That's going to give me 7.07 newtons. Now, right away, what I've done here, this is no longer a free body diagram, technically, because I'm breaking up this. This I would do in a separate drawing if I was asked for a free body diagram. All right. Now, this also is going to be 7.07 newtons. And then I can get rid of this one. Right, break it up into the x and the y. Now this one I'll also break up into the x and y. So 12 sine 135, 12 cosine 135. 12 cosine 135 gives me negative 8.49, and or cosine 135, and 12 sine 135 gives me 8.49 that way. Okay, so now I just add up all the forces. So the net force in the x direction is 7.07 minus 8.49. So that gives me negative 1.42 newtons, and the net force in the y direction is going to be 7.07 plus 8.49 minus 5. Right here, 2 up, 1 down, and so that gives me 10.56 newtons. Okay, so then we can say that F net, I can write sigma F, is negative 1.42 I plus 10.56 J newtons. And that's part A. Part B, what I'm going to do here is erase this now and go up. B is asking for the acceleration, and so I can express the acceleration this way. A, right, these are vectors so I can have the arrows over them. A is just F over m. So this is going to be negative 1.42 I plus 10.56 J over the mass. We're going to say the mass is 0.51 kilograms. And so the acceleration vector, now I need to get my calculator out. So this is going to be negative 2.8 I plus 20.7 J meters per second squared. All right, so that's part B. And then part C asks for the equilibrant. The equilibrant force, again, is just going to be, so FEQ is going to be 1.42 I minus 10.56 J. Again, what this means is if you were to add this force to the situation that's already there, then the whole body would be in equilibrium, and that would result in an acceleration of 0. And I think that's it for this first packet.